That's weird noises coming from next door. Okay. Anyway, so to review electron configuration, what we need to remember, there's a few things. First, we just kind of need to remember what atoms look like. So we've got the nucleus, which has the protons and the neutrons and all of that. Okay. And then surrounding that, in different locations, we have electrons. Okay. Now the fact is, these electrons can be just about anywhere. But they have certain areas where they're more likely to be. And these areas where the electrons are more likely to be, we call orbitals. Okay. And there's pictures of the different orbitals. Okay. They have different shapes depending on which orbital it is, whether it's the S, the P, the D, or the F orbital. Okay. Now, I don't care that you know the shapes. Okay? That doesn't matter at all. I'm never going to test you on that. So, we just need to remember S, P, D, and F. Now, electrons are going to naturally occupy the lowest energy level orbitals. They don't want to be in high energy states. It's like we said, why run when you can walk, that whole thing. That's what electrons are doing. They want to be in the lowest energy state. So they fill from the bottom to the top. Okay. Now electrons can jump up to higher orbitals, but they will tend to fall back down. When all of them are as low as possible, we call that the ground state. Okay. And that's what we are interested in when we talk about the electron configuration, the ground state. Now, if you remember, there's a picture in the book. This is back in chapter 5. So it's on page 156, and it's a bunch of different boxes. Okay, so it starts here with the 1s box. The 1s box is the lowest possible energy level. And then it will go up to 2s. And then next to that, we've got our p orbitals. This is the 2p orbital. And then it continues and it goes, and we're not going to draw the whole thing. That would take too long. But what happens is, like we said, the electrons start filling at the bottom. 2 electrons per box, per orbital. So every orbital can hold a maximum of 2 electrons. So we can put 2 here, 2 here, 2, 2, 2, 2, and so on. Now, because drawing that would take too long, we have the electron configuration notation that we talked about. And so, when we do electron configuration, the thing that we're most interested in, at least to start, the most important piece of information to start doing electron configurations is simply how many electrons are in the atom. So if we pick any element, any atom, So we'll pick, well, we'll just do phosphorus. Now, phosphorus is represented, symbol is P, and its atomic number is 15. Now, the atomic number tells us that there are 15 protons. But we're going to assume that this is a neutral atom, so how many electrons does it have? You're overthinking it. 15. Because remember, protons are positive, electrons are negative. So if it's neutral, if it has a 0 charge, it has the same number of protons and electrons. Okay? Today we're going to get into the instances of when it's not neutral. But anyway, so we have 15 electrons that we need to deal with. So we need to put them in the electron configuration. Now we don't want to have to draw this. So to know the order that we put things in, remember we write this out. Okay. And we do these downward diagonal lines. Okay. And you can see this if you wanted to look. It has it on page 160 in that box, problem solving strategy. Okay. So we start with our first line, 1s, which is right there. How many boxes are in all the s orbitals? One box. So how many electrons can an s orbital hold? Holds 2 total electrons. Okay. So we start with the 1s. All of these s's right here can hold 2 electrons. So we write 1s, that's the name of the orbital. And then we put a little 2 there saying we have 2 electrons. Okay. So our first 2 electrons go in the lowest energy level, 1s. So now we have 13 more electrons that we need to deal with. So we go to the next diagonal line here. And the next thing we hit, 2s. That means that's the next highest energy level. So we write a 2s. Once again, it's an s orbital. So it can hold 2 electrons. So we put another 2 electrons right there. And now we only have 11 more electrons to go. So we go back to our chart. We go to the next line, 2p. Now, when we look at the p orbitals, there are 3 boxes. And each one of those boxes can hold 2 electrons, which means in total through the p orbitals, we can put 6. Okay? The d orbitals have 10 and that has 14. Once again, I'm not really going to expect you to be able to do the d and the f orbital. They get a little bit weird. So, anyway, so we still have 11 electrons. We can completely fill this 2p orbital. So we put a 6 there. Means we have 5 left. So we continue down that line, and we hit 3s. Once again, we can put as many as 2. We have more than 2. We do that. And now we're down to 3 electrons left. So we finish this line, we go to the next one, 3p. Now, this could hold 6 electrons, but we don't have 6 electrons. We only have 3 left. So we put the 3 right there. Now, if we add up all of these numbers up top, if we've done it correctly, it'll tell us how many electrons we put in. Now, we should be able to add all those up to get to 15. Okay? So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. So, remember, we can shorten it with the noble gas configuration. So phosphorus, if we go up 1 and all the way over, that gives us neon, which is actually right here. So we could have just said neon, which gets rid of 10 electrons, which brings us to right here. And then we just do the 3s2 3p. When you write it this way, you can tell how many valence electrons there are.
Oh.
Yes.
One skip all the one there.
All of these?
Yeah.
Well, that right there, if you were to write out neon, it would be that.
Oh.
And so since we don't want to have to write all of that out, we just say neon, and then we finish it with phosphorus.
Neon is the one that's square.
Yep.
Okay.
This right here is neon. So we can use it as a shorthand. But we can see 2 plus 3 is 5 valence electrons. Now, I understand it's a little bit weird if you're not used to it. I get it. Doing electron configurations is one of those things where it's confusing, and then all of a sudden it clicks, and then you're just like, oh yeah, okay, I get it. Okay. That being said, you will have, a few electron configuration questions in the homeworks that you've turned in, and you may have 1 or maybe 2 on this coming test. And beyond that, we'll never talk about them again. So if these are confusing to you, don't let this convince you that the rest of chemistry is going to be impossible. Okay? Because like I said, these are weird until you're used to them. Once you get used to it and say, oh yeah, I understand how to do this, they're just weird. But once you practice with it a little bit and all of a sudden it just becomes a little bit more normal, then it's just like, putting numbers in a calculator. It gets to that point once you practice with it. But like I said, after this first test, we're never going to actually write out electron configurations again. So if you never get to the point where it's comfortable, well, you'll still be able to do well in chemistry. All right. If you still have questions about that, come see me during the study hall or send me an email or whatever. Get in touch with me and then we'll see if we can figure out where the confusion is and get it solved. All right. Today, we are going to finish up chapter 6. So earlier in chapter 6, we were talking about the periodic table. Okay? The book, like we said, it gives you some sort of history of how we got to our modern periodic table. This isn't a history class, so I don't really care that you know that. It's kind of interesting, and it does tell you a little bit about, just kind of why it looks the way it does a little bit, sort of that. But I'm not going to ask you history of periodic table questions on the test. So instead, we want to be able to use it. We want to know what sort of information it has and how to get that information. So if you remember, we can break the periodic table into all the different elements into basically 3 groups. Okay? We have metals, we have nonmetals, and we have the metalloids. Okay? Most of them are metals. Okay? Most of them are metals. All of the metals are going to be on the left side, and they include everything down below, all metals. Then we get this transition point. Well, on the one that we have up on the wall, it's a black line. The one in your book, it actually colors the boxes green for the metalloids. If you are looking at the one on the wall, everything that touches that black line except for aluminum is a metalloid. And remember, they have some properties of metals and some properties of nonmetals. It just kind of, for some of them, it depends on what environment they're in and just different things. But yeah. And then, of course, we have all of the nonmetals on the right side. Okay, there's really not that many nonmetals. Just a reminder, we do consider hydrogen a non-metal as well. But yeah. Just a couple vocabulary words that we want to make sure that everyone has. Up and down, group, side to side, period. All right. So let's start moving into some new material. Section 3 is all about different patterns that we see in the periodic table. Different patterns that we see. Now, the first thing that it talks about is atomic radius. So basically, how big is an atom? There are two different ways, 2 different techniques that we use in order to determine the radius of an atom. Okay? It pretty much depends on the type of bond that we're seeing. And this is on page 187. There's a picture, okay? Figure 10 right there. And it says, okay, these 2 different methods. The radius of a metal atom is 1/2 the distance between 2 adjacent atoms in the crystal. Okay, so metal, when we have all these metal atoms stuck together, okay, so if we have, well, let me grab an example here. We've got this piece of brass here. Okay. All the metal atoms are densely packed next to each other. Okay. So if we were to measure the radius of one, we would say, how far are these 2 atoms apart? And divide that in half. Now, brass isn't a great example because it's actually an alloy, but you get the point. So, When we have a non-metal atom in a molecule, okay, it's a little bit different. It's still basically measuring the distance between the two and cutting it in half, but because it forms a molecule and we're sharing valence electrons, which we'll get to in a little bit, it just looks a little bit different. The basic principle is the same. We take the distance between the nuclei and cut it in half, but you can see it just looks a little bit different based off the two. So just so you're aware. So when we talk about how big an atom is, remember, this goes back to what we started with. What does an atom look like? Well, it's got the nucleus in the middle and then electrons all around the outside. So most of an atom is empty space, but what we're measuring essentially is the distance, well, how big the electron cloud is. Because the more electrons you put in it, the bigger the electron cloud. That makes sense, right? Because we have to open up more and more orbitals that get bigger and bigger. Okay. So, it stands to reason then that the more electrons you put in something, the bigger it's going to be, right? Sort of. Sort of. Okay. If you look at page 188, it will show us the radii of these different elements. Okay. If you notice, let's look at lithium and beryllium. Okay. So lithium, well, it's right there on the periodic table. Okay. But you can also see it right there on page 188. So it is element number 3. So it has 3 electrons. Beryllium, element number 4. So it has 4 electrons. But looking at this chart, which one is bigger? Lithium. So why is the element that has fewer electrons bigger? Well, the reason for that goes back to the interaction between positive and negative. Remember, they're like magnets, okay? It's like a north and south pole on a magnet. They really want to be next to each other. So, if you have 3 protons and 3 electrons, okay, yes, there's an interaction between them, but if you have 4 protons and 4 electrons, it's a stronger interaction, okay? It's like adding another set of magnets, and it pulls down. So as you go across the periodic table from left to right, because you're adding more protons and more electrons, the interaction between them actually squeezes it down and it gets smaller. But, so if we go across number 2, so we got to neon. You can see that's the smallest right there. When we go to the next one, so we go to element 11, which is sodium. That's a lot bigger than neon. So what's happening there? Neon has a full valence shell. It has 8 electrons. Okay, we talked about the octet rule, how everything wants 8 electrons, right? You remember talking about that? Did we mention that? Yes? No? Maybe not enough. Okay, so I thought it was in this chapter. Maybe it's in this section. Oh, yeah, it's in this section. We'll get to it in just a second. So, it has that full valence shell. It doesn't want any more electrons. It can't have any more electrons in that valence shell, in that quantum level. So when you add another one, it has to be further out. And that's what makes it bigger. So as you go down the periodic table in the same group, the radii do get bigger because there's physically more electrons. But as you go across from left to right, since the electrons aren't being put into a new quantum level, they are squeezing everything down. Okay? So if the reasoning behind it makes sense, great. If the reasoning behind it doesn't make sense, just remember, in a single group going down, the radius gets bigger. In a single period, going from left to right, they get smaller. So, okay. So really, all of this is comparison. So examples of like test questions would be, which has a bigger radius, argon or krypton? Well, it's going to be krypton because as you go down, it's going to be bigger. But if we say, which has a bigger radius, phosphorus or chlorine, it's going to be phosphorus because remember they get smaller as they go that direction. Okay. So that's the kind of questions to expect on that. All right. Now the next thing, we want to introduce the concept of ions. So up until now, all of our atoms have been neutral. Okay, we've had the same number of protons and electrons. But that doesn't have to be the case. We can have a different number of protons and electrons. When that happens, it's called an ion. You can tell that you have an ion because it either has a negative or a positive charge, because you have the unequal numbers of protons and electrons. So if something has more protons than electrons, will it be a positive or negative ion? More protons than electrons. It's going to be positive, okay, because you have more positive pieces than negative pieces. Okay, so if you have more electrons than protons, then it's going to be a negative. Okay. Now, if you look at page 190, you can see the same rules for ions, or the same rules for the radius do not apply to ions. Okay. I want you to look at that and sort of see why, or see that it is different. It is different. Sorry, it's the end of the day. But we still need to talk about why. And this is where the octet rule is going to come in. So what you look at and you see is that if we start, with lithium, it looks like they're getting smaller, just like we would expect, until we get to nitrogen. And then it gets bigger again and starts going smaller. There is a reason for that. Okay? That's not just some random weird thing that's happening. And we will discuss that, why it is that way. Now, the book introduces this concept called ionization energy. Ionization energy is really just how much energy do you have to put something in or put into an atom to remove an electron. Okay? So these electrons are interacting with the protons. So they have this pull between the positive and the negative. And as we said at the beginning, you can make an electron go to a higher energy state. If you put energy into an atom with the right frequency, you can get these electrons to jump to a higher state. But if you put enough energy in, instead of just getting it to go to a higher state and then falling back down, you can actually get it to completely leave the atom. You can get an electron to completely leave. Ionization energy is, well, how much energy does that take? And for each atom, for each element, we can measure that ionization energy. Not only for each atom, but we can measure it for each electron. So there's a table on 192. It's table 5, successive ionization energies for the period 2 elements. Okay. So if we look, so lithium. Now these are, the units on this is kilojoules per mole. That probably makes no sense to you right now, and that's okay. It's a unit of energy. So for lithium, the first electron, so we're starting with 3, remember, lithium has 3 electrons. The amount of energy that you need to put in to get that first electron off, 520 kilojoules per mole. The second one jumps to 7,300. And then the third one, 11,810. Okay. So for every electron that we remove, the next one requires more energy. Requires more energy to remove. Okay. If you look at this table for a little bit, you'll notice on all of these, there's a spot where there's a big jump in energy. Okay. So for lithium, 500, 7,000 between first and second. For beryllium, it goes from 1,760 to 14,850 between 2 and 3. That jump happens for boron between 3 and 4, carbon between 4 and 5, nitrogen between 5 and 6, oxygen between 6 and 7, fluorine between 7 and 8, and neon between 8 and 9. So just a little comparison. To remove the first valence electron from lithium is only 520 kilojoules per mole. To remove the 9th electron from neon, you have to put in 115,380 kilojoules per mole. That's a lot more energy. A lot more. Okay? So why is this jump? This is where we get to talk about the octet rule. So how many valence electrons do we find in group 18 elements? 8. So octet, OCT, oct. That's the prefix for 8. Okay. Almost every element wants to have 8 electrons in the valence shell. They are the most stable when there are 8 electrons in the valence shell. That is the concept which is going to be the foundation for a lot of the things we do. Getting something to have 8 electrons, because that's where it's stable. Okay? Now, what we have found as we've done, chemistry over the years is that certain elements want to gain electrons to get to 8, and other elements want to lose electrons to get to 8. So let's, for example, let's look at chlorine. So chlorine is in group 17. So how many valence electrons does chlorine have? 7. Okay. Now let's just think about this. Don't even worry about chemistry. Let's just think about this rationally. If you needed to have 8 of something, and you had 7, what would you do? You'd add 1, right? So chlorine is most likely going to add 1 electron. So the most likely ion that we get of chlorine is a negative ion because we've added 1 electron. Now we can continue that. We move over 1 to sulfur. Now sulfur has 6. Okay. So what are we going to do to get to 8? We're going to add 2 more, right? We're going to add 2 more. So that becomes 2 minus. We can also do that with phosphorus. That one's going to add 3 electrons because it has 5. We're going to add 3 to get to 8. Now on the other side, if we look at sodium, now sodium has 1 valence electron, but remember, we've been building these electrons, okay? So the total number of electrons that we have in sodium is 11. This might be easier. I'll just draw it. So, in sodium, we've got our nucleus. We've got 1, 2 electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 1. So there's 11 electrons there. Okay. So what do we think is going to be easier? Should we add 7 electrons or take this one away and then that becomes the valence shell? Yeah, we're just going to take that one away. It's easier. So that means now we have 11 protons, but only 10 electrons. So it becomes a positive ion. Okay. If we look at right next to sodium, magnesium. Now magnesium is in the same situation, except there are 2 electrons. So we lose 2 electrons. Okay. Basically, if you want to determine, is this going to be a positive or a negative ion, you look at how many valence electrons it's going to have in its neutral state. Okay. If it has 3 or fewer valence electrons in its natural state, it's going to lose them. If it has 5 or more, it's going to gain them. If it has 4, it can go either way, but it's more likely to lose them. But to have an ion with 4 missing electrons or 4 extra electrons, those become pretty unstable because there's a lot of charge. They become very reactive. So that we don't see them very much. But they technically can happen. But like I said, we don't really see them much, so we won't do that. We'll mainly stay valence electrons 1 through 3, or 5, 6, and 7. Now 8, it has 8 electrons in the noble gas configuration, or noble gases. Well, it doesn't need to add or subtract any to get to 8. It already has 8. And that's why the noble gases really don't react, because they've got 8 electrons, they're happy. They don't need to interact in order to become more stable. So basically, what we're doing, we're taking something with its existing electron configuration and changing it so that the electron configuration matches the closest noble gas. Okay? That's what forming an ion really does. Okay? We are making it so that it has the noble gas configuration. Now, remember I said most atoms want 8. The notable exceptions, obviously, hydrogen and helium. Okay, hydrogen and helium. To get 7 more electrons on helium, or on hydrogen, to get 8 electrons out, the charge difference would just be too much. There's not enough positive charge to hold that many negative charges around it. So hydrogen and helium, they both actually only want 2. We consider their valence shell full at 2. We also are going to say that lithium with a +1, beryllium with a +2, or boron with a +3, we're going to say they are satisfied at 2 as well. But everything else from nitrogen on down, 8 electrons is the magic number. 8 electrons. Okay. All right. There's one last concept in this chapter. And it's the concept of electronegativity. Now we're going to introduce it here. We're going to come back to it several times. Remember, there's this interaction between the positive and negative. And just like magnets, there are two big things that determine the strength of this interaction. The first one is, well, how many particles are interacting? If you put more magnets, it's going to be a stronger interaction. The second one is the distance they are apart. Okay? If you have two magnets and you're holding them at arm's length, unless they're really, really strong magnets, you won't really see any interaction. But if you bring them closer together, you can start to feel that interaction. Okay? It's the same thing with these positive and negative charges. If they're close together, you can feel the interaction is strong. So these two things determine the strength of the interaction. Electronegativity is really a measure of this interaction. So we've measured how strong the interaction is between the nucleus and the valence electrons. How strong does it pull? Okay. And because of those two factors, the most electronegative element is fluorine, because they're close together. Okay, remember when we talk about ionic radius, all of those electrons and protons have smashed it down, so it's a pretty small atom, but it also has 9, which is more than any of these others, before it jumps to a bigger shell. So if you look at page 194, you can see a periodic table with measures of electronegativities. Now, it doesn't have the F block, and it doesn't have values for anything on the bottom here or the noble gases, mostly because they don't really react, and so we don't have electronegativity values. The ones down here, well, they're just not stable enough to measure. But you can see that there's a general pattern of, at the bottom left, that's our lowest electronegativity, and the top right is the highest electronegativity. So it increases from the bottom left going towards the top right, all the way up to fluorine, which is the most electronegative. Now, the electronegativity scale goes from 0 to 4. I'm not sure why they picked 0 to 4. That's just the numbers they picked. So fluorine, with its 3.98, is the most electronegative. Okay, like I said, we're going to revisit electronegativity several times. That concept will come back over and over in this class. So if it doesn't 100% make sense yet, we'll come back and revisit it. So don't stress about that. Any questions about what we talked about today? No? I know some of it was a little bit weird. I mean, it's just, the beginning of chemistry is a little bit weird because we're talking about things that you can't see. And so it's hard to visualize a lot of what's going on. As we get further on, we'll start talking about bigger picture things that we actually can see, touch, and, you know, visualize a little bit better. So if you feel like you need to be able to visualize what's going on, the first part of chemistry going to be a little bit tough, but then it'll get a little bit better. So right now we're just laying all of the groundwork, the foundation, so that when we start talking about these bigger picture ideas, you actually know what's going on. So, okay. Well, that's the end of today. We do have a short homework assignment for you. So we'll let you get started on that. I'll write it up on the board. And so once again, that's still in chapter 6. We haven't gotten into 7 yet. We will get into 7 next week. And chapter 7 is the last test, or the last chapter that we're going to have on this test.
Next Thursday, the review day.
Well, it's an 8A beat. It's an 8A class. So it would be
Next Wednesday.
I believe, let me double check.
Monday will be a test.
For your section, so for your section, Monday the 21st is the review day and the 23rd is the test. That's going to be your section. So we'll go through chapter 7 next week, and then the following week will be the test. I will get that review guide finalized and posted on LMS for you, so you can start taking a look at that. But anyway, so go ahead.